The sequential machine methodology, including register transfer and finite state machines, help us build fast and reliable digital systems. A register circuit reliably captures and stores a digital value. A clock signal is used to control when the register changes its state. The register value remains stable except during a small interval when the clock signals allow the capture of a new value. Combinational logic allows signals to flow through. When a combinational input changes, the result propagates through to the output. The unpredictability of changes to signals makes it difficult to design complex machines with combinational logic alone. The sequential model of operation is more abstract. It establishes order to the operation of the machine. The sequential model consists of a series of digital state values. A clock signal controls when each register reads a new value from its D input and stores that value. Sequential state is not continuous. The state jumps from one vector of digital values to another. The sequential machine imposes order on digital signals using registers. The register state changes at certain times governed by a clock signal. An event on the clock signal causes the registers to read their inputs and update their internal state. Changes on the combinational outputs will affect that state only at certain times. The result is a sequence of state values held in the registers. We can use a sequential machine to compute an output from previous states as well as the current inputs, something that combinational logic can't do. Sequential machines operate in parallel. Not only does all the logic in each stage operate in parallel, but two stages of logic also evaluate simultaneously. A pipeline CPU is an important example of the inherent parallelism of sequential machines. The clock is a special signal in a sequential machine. Controlling the characteristics of the clock helps us simplify the overall design. The clock signal is periodic. It has a period of T. Ideally, the clock should arrive at all points at the same time. But because wires and clock driver circuits have delay, registers at different points on the chip may see the clock transition arrive at different times. The clock signal also needs to be free of noise. Variations in the clock signal might cause other circuits to see a spurious clock event. High-performance design requires us to carefully analyze the distribution of the clock signal to be sure it meets our requirements. A D register is a basic form of a circuit that stores values in a sequential machine. The data input is D and the output is Q. A clock input controls the operation of the register. When the clock value goes high, it reads the D input and stores that value internally. Changes to the Q output into the register's internal state happen under the control of the clock. Here's a simple form of a CMOS register known as a dynamic latch. The gates of the transistors in the inverter provide capacitance that can be used to store a value. The inverter also amplifies the output signal. The latch's output is inverted from its input value. Access to the storage capacitance is given by a transmission gate. That's the combination of the N-type and the P-type in parallel. When the clock is high, both transistors in the transmission gate are on and the D input is connected to the storage capacitor. The capacitance can be charged or discharged through the D input. When the clock is low, the storage capacitor is isolated from changes at the D input. This simple latch is transparent. Changes at D propagate through to Q so long as the clock signal is high. We can narrow the window of transparency with a master-slave configuration of two latches. A single clock signal is delivered with opposite polarity to the two latches. When the clock is 0, the master latch is open and reads its input value. The slave latch doesn't change. When the clock is 1, the master latch closes, protecting its value. The slave latch opens, reading the new value and presenting it to the output. Thanks for watching.